the slope field jungle. Welcome to another calculus edition. Today we're going to call our notes slope field insanity. It's probably a little over dramatic. First, yesterday we talked about building slope fields, constructing the table values, and then putting all these little tiny line segments on our graph. And you're probably wondering, what else is there to slope fields? So, where do we go from here? Oh, well, first things first, I found this little comic today, and it really has nothing to do with today's lesson, but it was too good to pass up, and so I thought we'd throw it on here today. But basically, as we go through our notes today, continue to remind yourself this definition that we went over yesterday. A slope field is simply a graphical representation of the, note emphasis here on general solution. Because of all those different C values, there's an infinite number of solutions that are all quote-unquote parallel to each other, and the slope field gives us a great visual image of all of those in one snapshot. So we're going to go ahead, we're going to get more specific, and after we get our slope fields built, we're going to ask you some detailed questions about them. Okay, first things first. Here's the issue we talked about yesterday, is that these slope fields are so, I guess, easy, especially after you've practiced a couple, but at the same time they're time consuming, and we don't want to start to go so fast that we screw these up and make a careless mistake. But I want to challenge you here to construct this, fill out this table of values with all 25 slopes on it, and then transfer those slopes onto this little grid over here, and time yourself. Let's see, can we do it in 2 minutes? Can we do it in 2.5? Right around that time frame, without making any mistakes. Go ahead, hit pause, and see how fast you can do it. Okay, so here's what I got. Very carefully, we checked all these values, and we got a slope field that looks like this. Let's make sure that you've got your horizontal tangents going down the y-axis, except for that crazy one right at the origin. We've got vertical tangents going across the x-axis, and then just check your relative steepness throughout there. Make sure that your 2's are steeper than your 1's. Make sure your 1's are steeper than your 1/2's, etc., etc. And the more we practice, the quicker we're going to get naturally. So now we're going to go ahead and we're going to use this image of this slope field to answer the next 6 questions. Okay, our first question asks us to describe all the points within that xy plane for which the slopes are positive. Kind of a tricky question at first, but as we kind of dived into it and started to examine that slope field, I first noticed that every tangent line in the first quadrant was positive, and then every tangent line in the third quadrant was also positive. So the question is, okay, how do we explain this? How do I describe all the points that fall within those 2 quadrants? First of all, within the first quadrant, I would say that's every ordered pair such that both the x value is positive and the y value is positive. So we're saying both x and y are greater than 0. I'm throwing some squiggly brackets around it, and that's some fancy notation that you might have seen back in Algebra 2. And then we talk about the third quadrant. How do we describe the third quadrant? Well, we will say it's the set of all ordered pairs such that both the x-coordinate is negative and the y-coordinate is simultaneously negative. And that describes the third quadrant. So every ordered pair that falls within those 2 sets describes all the positive slopes. And a very similar question here, number 2. We want to describe all the points within that plane where the slopes are negative. And so generally speaking, we would say everything in the second quadrant had a negative slope. Everything in the fourth quadrant had a negative slope. Very similar to the last one, and you might want to try these on your own, but second quadrant would be every xy ordered pair such that let's say that x is less than 0 and y is greater than 0. And then for the fourth quadrant, I'm going to swing over here, make sure I got enough room. We're going to say it's every ordered pair such that the x-coordinate is positive and the y-coordinate is negative. And hopefully you can kind of read that. It's a little squished in there, but hopefully you can read it. Third question: when do we have horizontal tangent lines? Well, there was something that everyone had in common. Now, our slope field only had 4 horizontal tangent lines, and just ask yourself, what do all 4 of those have in common? I think you'd agree that what they have in common is that their x value is 0. So we're going to say every time that the x-coordinate is 0, with one exception. We're going to say that the y-coordinate cannot be 0. because at that one moment when both x and y were both 0, we ended up getting an undefined slope as opposed to a 0 slope. So I'm going to say every time x is equal to 0, with the exception that y can't be 0. That would describe all my horizontal tangent lines. Fourth question, we want to describe all the points where there's a vertical tangent line, and we have 5 of them on our graph. What do they all have in common? Well, every single one of them says that y is equal to 0. Anytime the y value is equal to 0, no matter what, we're going to have a vertical tangent line. Okay, here's a kind of a lengthy, interesting question. First of all, it says let y equal f of x be a particular solution to this differential equation with the initial condition that f of negative 2 equals 1. The first misconception is once we mention particular solution, everybody gets super excited. We separate the variables, we start to integrate, yada, 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 and we get our hands on the explicit particular solution where y is by itself. And that is just a whole bunch of unnecessary work. What they're really asking for is, all they're asking me to do is to write the equation for the tangent line of the graph at x equals, oops, I should say negative 2. That is a typo. Let's say x equals negative 2. So here's what you know. You already know that the y-coordinate is 1. The only thing you don't know is the slope. So what we're going to do is we're going to use our diff EQ, which is the first derivative in this case, to evaluate the slope. And here's the notation I'm going to use. I'm going to use a long line, and at the bottom lower right-hand corner, I'm going to say negative 2 comma 1. And that's my way of saying I'm going to evaluate the derivative at that point. We'll plug it in. I plug in the negative 2 for x, the 1 for y. We've got a slope of negative 2. Therefore, the tangent line is y minus 1 equals negative 2 quantity x plus 2. And I've answered their question. All they wanted was a tangent line, and here it is. Again, I want to emphasize no need to actually find a particular solution. There was just a lot of extra wording there to maybe throw you off track. Okay, we discussed earlier in the year that these tangent lines can be great at approximating the actual curve as long as we stay within the neighborhood of the point of tangency. And here they're asking me to use that tangent line to approximate f of negative 2.1. So we're just going to, perhaps now you've noticed it's a heck of a lot easier to just substitute that negative 0.1 instantly. I think our temptation is to try to distribute the negative 2, solve for y, all that jazz, and then plug in the negative 0.1 or 2.1, and I think that's just actually a lot harder. But anyways, we start to clean this up. Inside the parentheses here, we've got negative 0.1. If I multiply by negative 2, that's positive 0.2, and then we get y equals 1.2. So basically, we could say that therefore f of negative 2.1 is approximately 1.2. Not equal to 1.2, but approximately 1.2. My last question for you is, how would you answer this question? How would you determine whether that 1.2 was an over or an underestimate when we compare it to the actual value of f of negative 2.1? What we would have to do is what? Hopefully you've already answered this question in the back of your head. We'd have to take the second derivative, and we'd have to evaluate that second derivative at x equals negative 2.1 and see whether it was concave up or down. If we were concave up, our tangent line would be an underestimate. If we were concave down, the tangent line would be an overestimate. But again, it's all about the concavity, and it's certainly something we're capable of doing. I'm just kind of running out of time here, and I think you'd agree we could do it if we had to. Okay, we're going to practice one more problem very similar to the last one. This diff EQ is just a little more involved. Okay, but really not any more challenging than the last one we just did. Again, let's put ourselves on the clock. Let's see how quickly we can get this table filled out, get the slope field constructed, and then we'll go answer 6 similar questions. Okay, good time to check your work here. Again, we're just focusing on that famous phrase, relative steepness. Let's make sure our 3s are steeper than our 2s are steeper than our 1s, etc., etc. And just, again, be very careful that, our positive slopes are going up when read from left to right. Our negative slopes are going down when read from left to right. And again, something we talked about yesterday was just having something to aim at. For instance, let's pick one here. Let's see, I had to do a slope of 2 right here. This one right here had a slope of 2. So how did I even orient myself to try to, have a ballpark idea of what 2 was? All I did is I went up 2 blocks over 1, and I said, you know what, I'm going to aim right there mentally as I draw this line segment. Having something to aim at is really going to improve your accuracy as you go through these slope fields. Okay, first question. Describe every single point within the entire xy plane for which the slopes are positive. Now just keep in mind, we're trying to describe the entire xy plane as if it went from negative infinity to positive infinity in both the x and the y-axis. We don't want to limit ourselves just to this little rinky-dink slope field that we created by hand, even though it took us quite a while. We want to try to imagine that we went on forever and ever in all directions. Well, most of the points on our slope field are positive. What do they all have in common? Well, for every single one of them, the y value is less than 1. With the exception of what? What's the one exception? We're going to say x is not allowed to be 0. So any ordered pair that satisfies these two conditions, well, then the slope would be guaranteed to be positive. Every time the y value is less than 1, and while we make sure that x is not equal to 0, we'll have a positive slope. How about negative slopes? We have a few on our graph that had a negative slope. All the ones right across that top row, what do they all have in common? Well, every one of their y values is greater than 1, regardless of the x. If the y value is greater than 1, I can guarantee you the slope's going to be negative, it doesn't matter what x is. And also add that exception. Again, x is not allowed to equal 0. If it did equal 0, then we'd have an undefined slope, not a negative slope. Okay, where are your horizontal tangent lines at? There was a row of them right above the x-axis. What did every one of them have in common? Again, we're going to say anytime the y value is equal to 1, such that the x value is not equal to 0, then we're going to guarantee that there's a horizontal tangent line. And last but not least, where are all the vertical tangent lines? Those run right down the y-axis. So we would say, what do they have in common? Well, every one of them has an x value of 0. Again, before we go any further and dive into this question, I just want to reiterate, if I get to going too fast, by all means, hit that pause button, go back and rewind it, study that slope field, and make sure that you agree with all the answers that I've put down so far, because it takes a little bit of practice. There's no doubt about it. Okay, we're going to see another similar question. Again, they described y as the particular solution, such that the initial condition, f of 1 equals 2. Now notice within that sentence, at no time did they actually ask you to go find the particular solution. They never asked that. What they're actually asking me to do is to actually write the equation of a tangent line at the moment when x equals 1. And then you'll notice that when x equals 1, we already know the y coordinate's 2. The only thing we're missing is the slope. We're going to use our diffie-q to help us find that. Using this fancy notation, we'll say evaluated at 1, 2, and we'll go ahead and we'll plug it in. Substituting the 2 for the y, and then the 1 for the x. Let's see, what do we got here? We got a nice negative 1 for our slope. Therefore, our tangent line says y minus 2 equals negative 1 times the quantity x minus 1. Ladies and gentlemen, there she is. There's our tangent line. Okay, here's a new one. Now they want us to go ahead and use that tangent line to approximate f of 0.9. Just like we talked in the last one, we're going to instantly substitute that 0.9 into our tangent line. Let's see, just some very simple arithmetic here. We got negative 0.1, and it's so funny. This arithmetic is so simple, but when's actually the last time that you multiplied, things like this right here without the calculator? It's probably been a while. We got to turn our arithmetic portion of our brain on. We're going to get positive 0.1 there, hopefully. Therefore, y is equal to 2.1. Therefore, we could say, you know what? F of 0.9 is approximately 2.1. If they wanted to know whether that's an over and underestimate, we'd have to go calculate the second derivative using some intense quotient rule. We'd evaluate that second derivative at the 0.1, 2, and then check out the concavity. So certainly something we could do. Okay, things are going to start to get a little hairier here. We're going to talk about two key concepts that come up a lot on multiple choice questions. Number one, they're going to ask me to match my slope field to its diffie-q. Now remember, all diffie-q is, at least in our little world of calculus, we mentioned the other night that we're going to limit ourselves to just first degree diffie-q's only. Of course, when you get to college, you'll see much higher degree. But if we're only going to talk about first degree diffie-q's, then that means we're really only talking about the first derivative, dy dx. And dy dx describes the slopes of each tiny line segment. Okay, so again, the diffie-q is describing the slope at each little individual point. By comparison, check out the big difference here. Number 2 says we're going to match a slope field to its particular solution. Again, now this isn't going to say dy over dx equals. This is just going to say y equals, okay? We're getting ourselves an equation. The equation that we put right here is the equation that gets revealed when the slope field is fully constructed. What curve do you see being gently formed by the time you get all those little slopes drawn? So that's the big difference. We're going to practice a couple of these, and hopefully we'll make some sense out of them. So we're going to play a little matching game here. Now notice the directions are very small here, but we're matching the slope fields with the differential equation up here. So we're going to be very careful here, and I'm going to show you a strategy that I think is going to work really well for you. For instance, it can be a little overwhelming. You're staring at 4 crazy slope fields, you're staring at 4 crazy differential equations over here on the side, and you're like, where do I even start? Where do I even start? Well, I'm going to tell you, I'm going to let you in on a little secret. My favorite slope in the world, okay, let's write this up here in the corner. My favorite slope is 0 by a mile. So as I'm looking at this first graph, okay, slope field number 1, I just simply asking myself, can I find a line segment with a slope of 0? The good news is I've got several of them to choose from right along the line y equals 1 here. So I'm going to try to pick out a fairly obscure one. Maybe 1, 2, 3, 4. Maybe 4, comma 1. Would you agree right here at 4, comma 1 the slope is definitely 0? So here's what I'm going to ask myself. If I know that the slope at 4, comma 1 is equal to 0, I'm going to ask myself, which one of these diffie-q's, which one could I plug a 4 and a 1 into, respectively, a 4 for x and a 1 for y, and get an answer of 0? Okay? And I think what you'll notice, and perhaps you've already answered my question, if you go down here to D, and you notice if you substitute a 1 for that y, quite frankly, it does not matter what the x value is. You are guaranteed to get a slope of 0. So what we're saying is, on this diffie-q, every time that the y value is 1, you're going to get a slope of 0. And that matches up perfectly with this first diffie-q. So I'm going to say graph 1 matches up with equation D. That is a stone-cold lock right there. All right, I'm going to try to switch pen colors here. All right, I'm going to go to graph, let's see here. Oh, I forgot there's a big typo, and that's going to kind of give this one away. I forgot about that. Equation C right here, it's supposed to say xy plus x. That's going to give it away a little bit, but that's okay. We're just practicing right now. So as I look at graph number 2, I'm just saying, okay, are there any line segments that have a slope of 0? And I'm going to pick a fairly obscure one. I'm going to go 1, 2, 3, 4. I'm going to pick -4, comma -1. Do you agree that at -4, comma -1, the slope is definitely 0? So all I'm going to say is, which diffie-q could I plug a -4 and a -1 into to guarantee a result of 0? And if you look at equation C here, if I substitute a -4 for x, this is going to get a little messy here, a -1 for y plus a -4 for x again. If I clean that rascal up, I'm definitely going to get 0. And we could continue to test that theory. Maybe you're not sold yet. Maybe you don't think it's quite a guarantee. Maybe you could plug in 2, comma -1, test that theory. 4, comma -1, plug it back into the same diffie-q. See if you get slope of 0 again. But I don't think this diffie-q is going to disappoint you. I think C is going to match up really nice with graph number 2. All right, we're chugging. We're making progress. Let's see here. Graph number 3. I picked out a really nice point, 1, comma 4. And I said there is no doubt in my mind that at 1, comma 4 the slope is 0. And I'm just trying to figure out, is there a diffie-q that I could plug a 1 and a 4 into to guarantee a result of 0? And I tell you what, I fell in love with equation A right away. I plugged in, I substituted the 1 for x. And at that moment right there, it does not matter what you plug in for y. Do you agree with that? As long as that x value is a 1, you're guaranteed to get a slope of 0. Again, maybe you're not 100% convinced. Maybe you pick another point. Maybe you pick 1, comma -2. Plug him in. See if you get a slope of 0 again. Maybe you're really adventurous. Maybe you're really brave. Maybe you'll pick out, let's see, let's get real crazy here. Let's go -4, 2. You know, you look at a point -4, 2. Now, the slope's not 0, but we could say, you know, what is the slope right there? Maybe it's, you know, we're kind of estimating using the old eyeball test. You know, maybe you'd say the slope's -2. You know, and you start plugging those or that ordered pair into a bunch of diffie q's and, you know, see which one gives you a slope closest to -2. But again, that's not quite as an exact of a science because we just estimated the -2. We weren't 100% sure. But anyway, cutting to the chase here, I'm going to say that this slope field matches up with equation A. And at this point, well, we kind of know by default what the outcome's going to be. But I want to, you know, I want to follow this through and test it out a little bit. Here's what I did. I picked the point, -2, 1. What do you think the slope is right there? What's the slope at -2, 1? Hopefully you didn't say 0. Hopefully you said undefined. So here's the thing. Can I find a diffie q that I could substitute -1 and 2 into to get an answer of undefined? Well, let's take a look at B here. Plug a 1 in for y, plug a -2 in for x. You'll notice we definitely do get undefined. Therefore, that's enough to convince me today that equation B goes with the graph with 4. So that's how we match up a slope field with a diffie q. I want you to pick your favorite slope. Mine happens to be 0, and I strongly encourage you to use a slope of 0 too. That's a great place to start. Okay, this is our last slide for the night, so really buckle down, try to focus and finish strong here. Now, this time we're matching the slope field not with the diffie q, but with the equation that we think it represents. In other words, we are focusing on the solution. Okay, we're focusing on the solution. What curve do you see being developed according to this slope field? So rather than focusing on the slopes, I'm just going to focus on what curve do I see? I think this one. Do you see a slope field that kind of shows you a picture of y equals -x? I would say this one right here is a great image of what y equals -x looks like. So I'm going to say A matches up with graph number 2 here quite well. Okay, switch colors here real quick. Y equals -x squared. Do you see him? Yeah, I see that graph right here. If you just kind of follow the breadcrumbs, so to speak, that looks like a nice particular solution. So I think B matches up really nice with graph of 4. Okay, the other two equations are a little crazier, again, but I think if you study them a little bit, you definitely see e to the x being revealed right here. We start off very gently, and then we start to rise rapidly, so that's definitely y equals e to the x in my mind. So that's equation C goes with graph 3. And then last but not least, our good friend tangent. Do you see tangent anywhere here? Let's see. I see very steep lines, and then I see a gentle line, and then I see steeper lines. So right there, it looks like we've got our tangent curve. I think the trickiest one out of the 4 by a mile. But definitely, I think we agree we see tangent being developed there. So that looks like D for me. So these can be tricky, you know. Are we just ask yourself, am I matching the slope field with the diffie q, or am I matching the slope field with the solution? If it's diffie q, let's focus on slopes. If it's the solution, let's focus on the curve that you see hidden within the slope field itself. So there it is, ladies and gentlemen. If you're on your way to Florida, my best advice is to stock up on sunscreen. Otherwise, I'll see the rest of you in tropical Hamburg tomorrow. See ya.